In this video, we'll go over the basic principles of transistor amplifiers. Let's imagine that we start VGS at a value of 0 and start slowly increasing it. At first, VGS will be below the threshold voltage, and therefore the transistor will be in cutoff. In cutoff, there's no current flowing between drain and source, so the current labeled ID here will equal 0. As a result, there'll be no current flowing through the resistor RD, and no voltage drop across it. Therefore, the output voltage, VO, will simply equal VDD, the supply voltage connected up here. Shown over here in the bottom right is a plot of the output voltage, VDS, versus the input voltage, VGS, as we perform this sweep. So you'll see that as long as VGS is between 0 and VT, there's no current flowing, and VDS is equal to VDD. And the transistor is in cutoff in this region. Increasing VGS any further will cause it to exceed the threshold voltage, and so the transistor will turn on and start to conduct current. At first, the current will be very small, so there'll be a very small voltage drop across RD. VDS in this case will remain large, close to VDD, and therefore the transistor will be in saturation in this mode. While in saturation, we know that the drain current observes a square law. Specifically, ID equals 1/2 Kn VGS minus VTN, the threshold voltage squared, or we can use the overdrive voltage to simplify the expression here. The voltage drop across resistor RD will simply be RD times ID, and will therefore also be related to the input voltage VGS by a square law. Finally, we know that VDS will equal VDD minus the voltage drop on resistor RD. So it's VDD minus this square law quantity. So remember, all this analysis is only applicable when VGS exceeds the threshold voltage. So it starts at the point A on this plot, where the NMOS transistor enters the saturation region. From this point onward, it decreases parabolically, following the square law, until it reaches point B. Through this range, VDS is decreasing rapidly, with small increases in VGS. This is where this stage looks like an amplifier. At some point, VDS will drop so low at point B that VDS no longer exceeds the overdrive voltage. You can imagine extending a line with a slope of 1 from this point here, the threshold voltage. And when it intersects the curve, that's when we get to point B. At this point, the NMOS transistor is right on the border between saturation mode and triode. Further increases in VGS will tip the transistor into triode, the square law will no longer apply, and the shape of the curve will change. We'll have to perform a whole new analysis for this part of the curve. So in summary, this case 2 applies as long as VGS is large enough to turn the transistor on, that is larger than the threshold voltage, and at the same time while VDS exceeds the overdrive voltage. That's true in this part of the curve between A and B, and in this region, the shape of the curve is parabolic, following this expression here. Finally, we enter this third part of the curve, where the NMOS transistor enters triode. This occurs with VGS larger than the threshold voltage and the output voltage, VDS, less than the overdrive voltage, VOV. In this part of the curve, beginning at point B and going to point C, where VGS equals VDD, the drain current is no longer governed by the square law in saturation. Instead, it's governed by this triode equation. Now, you may recall that when VDS gets very, very small, in this part of the curve, this term becomes negligible. In this case, you end up with a drain current that's just linearly related to VDS. In this part of the curve, the drain source connection looks like a simple resistance RDS. You'll notice that this part of the curve flattens, so the relationship between the input VGS and the output VDS isn't as steep anymore. Therefore, it's not going to be as useful as an amplifier. You can see that it flattens out by recognizing that VDS can never reach zero. If it did, this expression would predict that the drain current is also equal to zero. But if the drain current were equal to zero, there'd be no voltage drop on RD, and therefore VDS would be VDD, which would violate our original assumption that VDS is zero. So instead, the drain current increases, but VDS never quite drops all the way to zero. If it never gets to zero, it must curve and flatten out, as shown in region 3 of the plot when the NMOS transistor in triode. Thus, the steepest slope on this plot is obtained while the transistor is in saturation. That's going to be the mode we focus on for use of the circuit as an amplifier. Next, let's consider this NPN BJT amplifier, which is very similar in form and function to the NMOS amplifier we just considered. Here we see the emitter is connected to ground, the input is applied between base and emitter, VBE, and the output is taken at the collector. As with the NMOS amplifier, we can observe in the input-output relationship here 3 distinct regions. First, for small VBE, we see the transistor is in cutoff. For the NMOS amplifier, the transistor was in cutoff for any input voltages below the threshold voltage of the transistor. The threshold voltage of MOSFETs can vary depending on their construction. The difference here is that with a BJT, we've got a PN junction, and as long as that's made of silicon, the junction and the transistor will start to turn on when VBE exceeds around 0.5 volts. So it's always around 0.5 volts that some current starts to flow here. As it does, some voltage drop arises across the resistor RC. The collector current is exponentially related to the base emitter voltage. And so, for small increases in VBE in this region, this voltage drop RC times IC increases rapidly, and thus we see the output voltage drops quickly in this range. In this region of operation, the BJT is in the active mode, and because of this high slope, it's going to be very useful to operate the amplifier in this mode for amplification. Now, clearly it's going to be a negative gain here since the slope is negative, but nevertheless, it's a very steep part of the curve. Finally, once the output voltage VCE drops low enough the NPN BJT will enter saturation. This arises at point B and is analogous to the point in the NMOS amplifier where the transistor entered saturation. Now, the point at which the NMOS transistor entered saturation depended on VOV, the overdrive voltage of the transistor. Whereas in the case of BJTs, this is always going to happen at an output voltage of around 0.3 volts, give or take a few millivolts here. From that point on, the collector current will not increase as quickly, and so just as was the case with the NMOS amplifier, the output voltage will this curve will flatten out, and we won't see any further gain. Finally, you'll notice that the plot here is not continued all the way up to very large values of VBE. And the reason, again, is because of the exponential voltage current relationship in a BJT. If we increased VBE very far beyond 0.7 volts, we would very quickly start seeing a very large amount of current flowing into the base through both forward bias junctions. And the circuit would, the transistor would quickly overheat. So in practice, for practical values of current, it's really only worth considering this input-output characteristic up to values of VBE a little bit greater than 0.7. So again, the key point here is in this region where the transistor is in active mode, the slope of this input-output relationship is very steep, is governed by this exponential IV relationship. That's where we're going to bias the circuit for use as an amplifier. Having seen that both the MOSFET and BJT amplifiers are quite similar in form and function, let's return to the NMOS amplifier for our discussion. So again, we saw an input-output relationship like this, and the steep part of the curve arose when the transistor is in saturation. So if we're going to want to operate this circuit as an amplifier, we're going to have to establish an operating point in that region. We've identified a point Q in that part of the curve. And you'll see that at this point, the input-output relationship has a relatively steep curve. Now, what we want to do is apply a DC voltage to the gate that establishes an operating point at Q. And then we're going to superimpose on that DC input voltage a relatively small signal. Doing so will allow us to deviate from the operating point Q and give rise to larger changes in the output voltage than what we observe at the input, or than what we apply at the input, I should say. Now, the DC analysis of the circuit shown here is something we've already considered. It can be solved for, since we know we're in saturation, using the square law IV relationship of the MOSFET. Neglecting channel length modulation, we can say that ID is half Kn VGS minus VTN squared. And we also know that VDS equals VDD minus ID times RD. So usually using those two relationships, we can relate the input voltage VGS to the output voltage VDS here and find the operating point Q. We'll also then know the drain current flowing in the transistor ID, which will be important. Here you see the NMOS amplifier again. This time we have superimposed on the DC source VGS a time varying quantity VGS that represents the signal to be amplified. So you may recall our notation here, and it's important to keep these definitions straight. Variables that are lowercase with uppercase subscripts, such as VGS here, are the total quantity, and they're the superposition or sum of the DC operating point quantity, which is all uppercase, and the so-called small signal superimposed on it, which is all lowercase. So VGS total, this VGS here, all uppercase, that's the so-called DC operating point. OP for short. And then here's the all lowercase small signal superimposed on it. Similarly, we define the output at VDS as the superposition of the DC operating point, all uppercase VDS, which we calculated using the square law on the last slide, and a small signal quantity, all lowercase VDS, which arises in response to the small signal input, all lowercase VGS. We can make similar definitions for the drain current flowing. It's got a DC operating point part, and a small signal part, all lowercase. Now, by ensuring that the small signal deviations away from our operating point Q are small enough to keep the input-output variables within this linear range here, then we can imagine that the small signal quantities, lowercase VGS and uppercase VDS, are related linearly just by a multiplicative gain constant. And of course, the multiplicative gain that relates the small signal quantities is nothing more than the slope of this input-output curve. So the slope of the curve evaluated at the operating point Q is the gain, the voltage gain of this NMOS amplifier for the small signal quantities VGS and VDS. As you can see here graphically, there are limits over which this small signal assumption or approximation is valid. Obviously, if the applied input VGS is large enough to cause the transistor to enter this region or this region, then the input-output relationship no longer observes this linear relationship, and it's not really serving as a very good amplifier anymore. So one criteria for the designer to select the operating point by applying the appropriate DC operating voltage VGS would be to make sure Q is centered in that range. That would allow for the maximum possible signal excursions while still keeping the transistor operating in saturation mode. We'll discuss that further later. So with an operating point established at Q, we're interested in finding the slope or small signal gain here, which we've called AV. Now, the shape of the curve in this region is governed by square law. So here we have the drain current ID, again, assuming the transistor's in saturation. And the output voltage VDS is just VDD minus that drain current times RD. The slope of the curve is found by taking the derivative of this expression with respect to VGS. So if we do that, we'll see that we've got negative 2 times half Kn RD VGS minus VT. And again, we're interested in this evaluated at the operating point Q. Now here's where our notation is important to keep straight. At Q, the lowercase v uppercase GS is equal to the uppercase VGS, equal to its DC operating point value here at the point Q. So we can substitute that in. We've got 2 times a half, so those cancel, and we get a little simpler expression here for the slope evaluated at Q. This quantity VGS minus the threshold voltage is in fact the overdrive voltage evaluated at the operating point. So let's use all uppercase variable, all uppercase letters to denote that quantity VOV. So based on this relatively simple expression, we see that the small signal gain is increases with increasing overdrive voltage. So that's not surprising because it means that as we increase the overdrive voltage, we would be shifting the operating point this way on the curve. And since this part of the curve has a quadratic shape, it's not surprising that this curve gets a little steeper as we approach B. But then we'll have to be careful because if we go beyond the point B, it'll start, the square law will no longer apply because the transistor will enter triode, and then we'll have a different expression for the gain, and it'll start to decrease. The other term of interest here that we have control over as a designer is the value of RD. Larger RD will give us more gain. Finally, here we have the NPN BJT amplifier again. Here we've superimposed on top of the operating point VBE our small signal, all lowercase, just use SS for short for small signal, our small signal, all lowercase VBE. And we may be interested in relating the small signal input VBE to the small signal output, which is superimposed on the DC operating point at the output. So again, if we want to use this circuit as an amplifier, we likely want to bias it at the operating point Q somewhere in the region where the transistor is in active mode. And if we do so, the input-output relationship is governed by this exponential equation up here. And we can find the small signal gain by taking the derivative of the curve and evaluating it at the operating point Q. If we do so, we will see that AV is given simply by negative RC or VT IS e to the VB over VT, again evaluated at Q. When we evaluate at Q, we can substitute our all uppercase VBE, the operating point value of VBE. We substitute that in and we get an expression like this, RC over VT IS e to the VBE over VT. Now, interestingly, you notice this part of the expression here is nothing more than the DC collector current, IC, that flows. Right? Again, collector current can also be written as the sum of a DC operating point part and a small signal part. Little difficult, this is where the notation gets tricky. It can be a little difficult to distinguish uppercase and lowercase letters like C, but so you have to watch out for that, and hopefully it's clear from context. In any case, end up with, we can rewrite the gain expression now in terms of that bias current, IC, and you get a relatively simple expression here for the gain of the BJT amplifier. Again, a key point here is to ensure that the collector current is not so large that the voltage drop across RC kind of compresses VCE all the way down into saturation, doesn't push it beyond this point B here. If it does, then this these relationships no longer hold and the curve starts to flatten and we get much less gain. Qualitatively, because this input-output relationship is exponential in nature, you can generally get steeper slopes and thus higher small signal gains using BJT amplifiers. On the other hand, the thing to watch out for is that means that the circuit operates linearly over a narrower range of input voltages. So it requires some different techniques for establishing an operating point Q that's in this sort of sweet spot where the transistor is in active region.